Hello, my name is Vishal Kumarja, studying in Sri Venkateshwara College of Engineering. Today's topic is concept of sparse matrix in data structures. Representation of sparse matrix. Linked list representation. In this representation, each non-zero element of the sparse matrix is stored in a linked list. Each node of the linked list contains the row index, column index, the value of the non-zero element. Array of lists representation. In the representation, an array of lists is used to store the non-zero elements of the sparse matrix. Each row of the matrix corresponds to a list and each node of the list contains the column index and the value of non-zero elements. Types of sparse matrices. Compressed sparse row. Store non-zero element in each row along with their column index. Efficient for row-wise operation and accessing elements by row index. Compressed sparse column. Store non-zero element in each column along with their row index. Efficient for column-wise operation and accessing elements by column index. Dictionary of keys. Store non-zero elements as key value pairs in a dictionary. Efficient for random access and modifying individual elements. Coordinates list. Store non-zero elements as tuple of row column value. Efficient for constructing sparse matrices and sparse matrix arithmetic. Operations of sparse matrix. Sparse matrices are matrices that have a large number of zero elements. Due to their sparse nature, special operations can be performed on them to optimize memory storage and computational efficiency. The following are some common operations that can be performed on sparse matrices. Common operations. Addition. Sparse matrix can be added together by adding the corresponding elements of the matrices. Only non-zero elements need to be considered, which reduces the computational complexity. Multiplication. Sparse matrices can be multiplied using specialized algorithms, such as the sparse matrix vector multiplication or the sparse matrix multiplication. These algorithms take advantage of the sparse of the matrices to reduce the number of operations required. Transpose. The transpose of the sparse matrix can be computed by swapping the row and column indices of each non-zero elements. This operation can be performed efficiently by iterating over the non-zero elements. Sir, scalar multiplication. The sparse matrix can be multiplied by a scalar by multiplying each non-zero element of the matrix by the scalar value. This operation can be performed efficiently by iterating over the non-zero elements. Conversion to dense matrix. A sparse matrix can be converted to a dense matrix representation by filling the non-zero elements. This operation can be useful for certain computation that requires dense matrix multiplications operations. Applications of sparse matrices. Sparse matrices which contain mostly zero elements have various applications in different fields. Graph theory. Sparse matrices are commonly used to represent graph, where nodes are represented as a row and columns, and edges are represented as non-zero elements. Natural language processing. Sparse matrices are used to represent the frequency of word in a document, where each row represents a document and each column represents a word. Image processing. Sparse matrices are used to store and manipulate images, where each row represents a pixel and each column represents a color channel. Machine learning. Sparse matrices are commonly used to represent high-dimensional data, such as text data or image data, where most of the features are zero. Advantages and disadvantages of sparse matrices. Advantages: efficient storage. Sparse matrix optimize storage space by only storing non-zero elements, reducing memory requirements. Faster operations. Sparse matrices enable faster operation by skipping unnecessary calculation on zero elements. Reduced computational complexity. Sparse matrices reduce the computational complexity of matrix operations, leading to faster processing times. Disadvantages. Increased complexity. Sparse matrices introduce additional complexity in terms of indexing and handling empty elements. Slower access time. Accessing individual elements in a sparse matrix can be slower compared to dense matrices due to the need for additional indexing operations. Limited appli- applications. Sparse matrices are most effective when the matrix contains large number of zeros element in case where the matrix is mostly dense. Using a sparse representation may not be provide sufficient benefits. Comparison with dense matrix. Sparse matrix and dense matrix. Sparse matrix contain mostly zero values resulting in efficient storage and computation. Ideal for representing large datasets with many zero values. Requires less memory compared to dense matrices. Dense matrices contain mostly non-zero values resulting in higher memory usage. Suitable for small datasets or datasets with few zero values. Requires more memory compared to sparse matrices. Conclusion. Key points. Sparse matrices are used to efficiently store and manipulate large matrices with mostly zero values. Sparse matrices can be represented using different data structures such as linked list, arrays, and hash tables. The choice of the data structure depends on the specific operations to be performed on the sparse matrix. Common operations on sparse matrix includes addition, multiplication, and transposition. Sparse matrix algorithms can sufficiently reduce memory usage and computation time compared to dense matrix algorithms. Thank you for watching my video. Do like and subscribe.